All right. So we've talked about interrupts, and you've done homework on interrupts. And from what I've seen so far on the homeworks, it looks like people basically understand these, and you're doing your lab on interrupts. This is a part of most computer systems you'll encounter have a way to deal with interrupts. And it's pretty much the same procedure in different machines. You have to enable interrupts, usually per source and globally. You may have to set up additional characteristics, like do you want to interrupt on a rising edge or a falling edge, do you want a high priority or low priority, and so on. And then somewhere there's a particular location to which the CPU will jump when an interrupt occurs. And inside the interrupt handler, you do whatever you need to do to respond to the interrupt. You usually have to clear an interrupt flag and then come back from the interrupt somehow with a return or a Redfee or something like that. The specifics will change from architecture to architecture, but those basic steps will be present pretty much any time you're working with interrupts. And it happens with software interrupts as well. When we do graphical interfaces in CSE 223, we're basically doing software interrupts. What happens when you click a mouse? Same kinds of things. You have to enable the system to act a certain way when a mouse click occurs. You have to tell it where to go in your code when that event happens. You have to do certain things inside there, and then you have to come back from that event handler. So this is something you'll encounter again and again. The last comment I want to make on interrupts before we go on to timers is be aware of side effects. So side effects are things that you don't want to have changed in your interrupt code. For example, you're writing code that when you get an interrupt, you should increment file register 80. Okay, that's a change that you want to have happen. You want that file register to be incremented. But maybe when you get an interrupt and you call your interrupt code and you come back, maybe the W register has also changed value. That's what we would call an unintended side effect. And if it's possible that you were running some code that did something like this, move 55 into the W register, and then move that into, I don't know, let's say port A. And maybe at location 8, you go to some high priority interrupt handling code. And what are you doing here? I don't know, maybe you do, you know, maybe you move port B into 0 and you do an AND with that, and you do a branch of 0 something and you do something else, and eventually you say Redfee. So it's a synthetic example. Don't worry too much about what it's supposed to do, but the idea is you've got an interrupt handler that will check, you know, some input bit on port B and do something based on whether it's 0 or not. Now suppose your main program, you've set up interrupts and so on, you're executing this instruction here which says put a 55 into W and then copy W to port A. And suppose that right here, after you've done the move LW, but before you do the move WF, you get an interrupt. And the processor saves the address of this instruction so it can come back, it jumps over here to location 8, it goes to HPRI, it starts executing this code. Well, what's it do right here? It takes the contents of port B, puts that into the W register, ANDs it with a bit mask, so now you have a W register which is equal to either 0 or 1, does some other stuff, you do a Redfee. What's the value of W now? It's either 0 or 1. It's the value that you last had inside this chunk of code. There's no notion of like local variables, right? If I change W in my interrupt handler, when I return, the value of W will be whatever I set it to in my interrupt handler. And I just broke my code. Because my code was supposed to put 55 hex out to port A, instead it's going to put some totally random value into port A. So in general, with interrupts, you want to be thinking about unintended side effects. And you want to make sure that whatever you do in here doesn't potentially upset something that you might have been doing in your main program. And that can be challenging because we have so many different things that we can do in our interrupt code. Let's take a look at the data sheet. So Redfee, which we've just been typing as Redfee, actually takes an optional operand, which is called S. And S is a flag which is used to say, let's restore the values of certain things from what are called the shadow registers. Okay, so here's the really brief version of this. Whenever you get an interrupt, the current W register is saved in a temporary variable called W shadow. The status bits are saved in a temporary location called status shadow, and the bank select register, which we mostly don't care about, is saved in something called bank select register shadow. These are three registers that temporarily store the values of W, the status bits, and the bank select register. And when you say Redfee, if you say Redfee space 1, it will restore these three registers from these temporary holding places. So down here, if I say Redfee 1, my problem is solved. Because when I got the interrupt, the current value of W, which was 55, goes into this temporary holding place called W shadow, WS. And yeah, I changed W in here, I copied port B into it, I ANDed with a bit mask and so on. But when I say Redfee 1, the processor, before it returns, will take the contents of the shadow register, copy that back into W. So when I return here, W is still 55 hex. So that's one really easy way to deal with possible side effects to the W register and the status bits, is to use Redfee 1. And the status bits are even more tricky to work with, right? So suppose I say something like move port A 0 and LW. I want to check bit 7 of port A, and I say branch if not 0. Good stuff. And suppose I get an interrupt right here. Well, normally I go into my interrupt code, I do a bunch of stuff. Most of my instructions in my interrupt code change my status bits. When I Redfee, I'm going to come back here to this branch if not 0. What am I branching on? I'm no longer branching on the result of this operation. I'm branching on whatever the last instruction was in here that touched the 0 bit. That's real hard to debug, by the way. Okay, so if I do a Redfee 1, when I get this interrupt, the other thing that happens is my status register goes into the status shadow register. And then when I Redfee, the status bits, whatever they were at the time that the interrupt happened, get restored. So now when I come back here and I do a branch if not 0, I'm branching on the status bits as a result of this instruction. So Redfee 1 is a nice way to deal with that, up to a point. The problem is there's only one set of shadow registers. And remember, if you get a low priority interrupt, while you're in your interrupt code, it's possible to get a high priority interrupt. And if you have nested interrupts like that, what's going to happen? Your first set of shadow registers are going to get overwritten. So if we don't want to trust the shadow registers, or if we need to deal with nested interrupts, what can we do? Make yourself a file register somewhere for saving the status register, and say move ff status comma my status save. And then move the W register, my W save. Do your business. When you're done, move from my W save into the W register, and then move FF, my status save, comma status, and then do your Redfee. Redfee does not affect any status bits. It says that somewhere in here. Right, so Redfee doesn't affect any status bits other than the global interrupt enable bits. Okay, this is pretty nuanced, but it's just something I want to mention because you'll probably bump into it somewhere down the road. So it's something to keep in mind. Do only the things that you cause, only the changes that you actually intend to cause in your interrupt code, basically. All right, so new topic. The topic is timers. Now, hold on a second, let me hop into my other Zoom. Hold on one sec. Alright, so I'm on my other Zoom window. If you need to send me a chat message, do it through the one that says co-host, because that's the one I can look at. Alright, so let's talk about timers. So we've already gotten some experience making delay loops by basically just doing nothing, but doing it for a long time. So decrement, file register, whatever, branch if not 0 back to the previous decrement statement. That takes time, right? It takes 3 cycles, it takes 4 if we throw a no-op in the middle. And depending on the initial value of the thing we're decrementing, we can cause that loop to happen a certain number of times, and we can calculate how much wall time will pass from the beginning of that loop till we get out of the loop. And so we've been using this kind of boilerplate code for a 1/10 of a second delay by loading a 195 into W and then counting down to 0. And that works reasonably well, but there's a few problems with it. One problem is if we wanted to get a longer delay, we need to start counting at a much bigger number, and the largest number we can put into a single register is 255. So we need to have 2 or 3 file registers and do 16 or 24-bit subtractions, and that gets complicated. The bigger problem with these delay loops, though, is that while we're waiting for this time period to pass, our CPU is busy doing nothing. It's busy counting down in a loop or in a pair of nested loops. And maybe while we're waiting 2 seconds for the traffic light to change, we want to be doing something else. Maybe we want to be monitoring traffic somewhere else, or we want to be sending information somewhere or whatever. And it's expensive CPU-wise to spend your time just waiting, for 2 seconds to pass or 2 minutes to pass, right? That's inefficient. So most processors, including the PIC, have 1 or more hardware timers built in. And so what we want to do now is we want to look at these hardware timers and understand some basic information about how to use these to generate timing events. And this is stuff that can be tricky to do in the simulation because, you know, simulated time is different from real time. We have the stopwatch feature in the simulator which will help, but we can't change the underlying clock frequency easily in the simulator, even though there's buttons that are supposed to let you do that. So we have to take some of this on faith and play around with it. So the way timers work on most of these processors is a little peculiar, but we can make analogs to some degree with what we do with a regular timer. So if you have a stopwatch, right, like a countdown timer on your phone, or, you know, an old mechanical stopwatch, what do? You load in some initial time. So you set your countdown timer to 15:00, which means 15 minutes 0 seconds. And then you hit the start button and it starts counting down, 14:59, 14:58, 14:57, all the way down to 0. And then when it gets to 0, it starts beeping at you. And when it's done beeping, you hit the stop button, right, when you want it to stop beeping. And you're done with your timing event. Okay? Similar things happen in the PIC processor with the timing subsystem, but with some key differences. So let me take you through a bit of the data sheet first. So there's 4 chapters on timers, 11, 12, 13, and 14. Mostly we're going to talk about timer 0, because it's almost identical to timers 1, 2, and 3. Timer 2 is very peculiar, though. We'll talk about that more next week. But timer 0 is as good as any to look at. And just like dealing with interrupts, the timer interface is through a bunch of special function registers. So T0 control 8-bit register that we can use to control certain things. And there's a pair of registers called timer 0, low, and H. These are 2 registers that we treat as a single 16-bit register. We've seen this a few times in other instances. Timer 0H is the upper 8 bits of this register. Timer 0L is the lower 8 bits. So you're going to see me use the word timer 0. And there is no register TMR0, but this is actually a composite of 2 8-bit registers. Timer 0 high and timer 0 low. So for example, I may say something like load hex FE23 into timer 0. You might see a comment like that in your code. There is no timer 0 register. There is no instruction that loads a 16-bit register value into a register. What this would mean is let's load a 23 into timer 0L and let's load an FE into timer 0H. Okay? But that's a lot of muck to get bogged down in, so I'll just talk about timer 0, and if we need to load a 16-bit value into it, we have to understand that means loading the 2 pieces one at a time. Okay, so that's the first thing to try not to get tripped up on. It's a 16-bit register, but I'll just treat it as a register. And there's a nice picture here of how timer 0 works, and these are almost the same thing, so let's just look at this first picture. So this is that timer 0 register, and it counts up. Okay, it's just like a counter from one of our labs in Engineering 250. Every time that this input ticks, the value in this register goes up by 1. And when this register goes as large as it possibly can and then overflows back to a 0, that's when the timer generates an interrupt. Okay, so the interrupt is the alarm clock going off. Okay, so you want to understand this level of it first. Three things. There's a register that's counting up each time that something ticks its clock. Each time we get a tick, the value in here goes up by 1. And when this overflows, right, when it goes back to all zeros, the system generates an interrupt request. So timer 0, interrupt flag gets set. If you can understand those three things, you're 90% of the way done with timers. Even though we'll be talking about them for a week. Okay, three things. There's a value in here. Every time this line ticks, the value gets incremented by 1. When it rolls back over to 0, it generates an interrupt request. Everybody got that?
Could you repeat that?
Sure. So there's a value inside this register. There's a clock line here, and every time the clock ticks, this value gets incremented by 1. And when this value gets incremented so many times that it overflows, it goes back to 0, the system generates an interrupt request. Okay, that's 90% of timers right there. So with just that, we can ask the following question. Suppose I want to generate an interrupt after a certain amount of time. How can I do that? Well, I need to know two things. I need to know how often does the clock tick to increment this value. And let's just suppose that every microsecond the clock ticks and this value gets incremented. So let's do an example. Totally fictitious. So suppose the clock ticks and increments timer 0 every microsecond. And let's suppose timer 0 overflows at 256. So let's just suppose timer 0 is 8 bits for now. It's an 8-bit register. And let's say that if it's 8 bits, that means it overflows at 256. You can store any number in an 8-bit register from 0 to 255. But if the timer register has 255 in it and the clock ticks, it will overflow. So let's look at some scenarios. Suppose we load a value of 255 into timer 0. Move LW 255, move WF timer 0L. So we put a 255 in here. And remember, we're assuming the clock ticks every microsecond. So after 1 microsecond, the clock will tick. This register will get incremented from 255 to 256, which is an overflow. And it'll generate an interrupt request. So if you set timer 0 to 255, you get an interrupt request after 1 microsecond. Does that make sense to everybody?
Yep.
So suppose I set timer 0 to 254. When will I get an interrupt request?
2 microseconds.
2 microseconds. Why is it 2 microseconds? Because if I put a 254 into this register, after 1 microsecond it will increment to 255. After a second microsecond it will increment to 256, which is an overflow, generates an interrupt request. If I set timer 0 to 250, when will I get my interrupt request? Well, 1 microsecond it'll be 251, 2 it'll be 252, 3 it'll be 253, 4 it'll be 254, 5 microseconds it'll be 255. After 6 microseconds it'll increment to 256, generate an interrupt request. So there's a formula we can make from this, right? If we want to interrupt after 10 microseconds, what value should we load into timer 0? Actually, it's going to be 246. Yeah. There's always a fence post issue there. We're going to be off by 1, give or take sometimes. That's okay. But yeah, 246. So our formula looks like, since it overflows at 256, subtract how many microseconds you want. That's the initial value we should put in there. So if I wanted to interrupt after 50 microseconds, I should initialize this register to 206. And then after 50 ticks, 50 microseconds, it'll hit 256, overflow, generate an interrupt request. Alright, so that's the next piece of it that you want to get your brains around, is this idea that this thing is counting up, and by controlling what value we start the timer at, we can control how long it takes until an interrupt occurs. And now you're about 95% of the way there. Everything else is just annoying details now. But conceptually, you've got the whole essence of the timing subsystems. Because
how many fractions of a second is microsecond again?
There's 1,000,000 microseconds in a second.
Okay.
But I picked a microsecond totally at random. Nothing really to do with reality. But we're going to make that a realistic number soon. So that's this part of the timing subsystem, right? Something is generating ticks that increment this register, and when it overflows, we get an interrupt request. And remember, an interrupt request does not mean you're going to get an interrupt. It means it's going to set this timer 0 interrupt flag bit. If we've also set timer 0 interrupt enable, and if we've globally enabled interrupts for whatever priority level this interrupt is, then we'll actually get an interrupt request. I mean, we'll actually get an interrupt, and we'll jump to location 8 or 18. Okay, but this is just saying, hey, I would like an interrupt. And then you have to go back to the whole interrupt subsystem and deal with all of those registers to set up the enable flag, priority, all of that stuff. I'm not going to go into that today. I want to concentrate on this particular piece of the timing system. All right, suppose we wanted a delay of more than 256 microseconds. Suppose we wanted to wait 500 microseconds. Well, we can't subtract 500 from 256 and initialize this to negative 256 or something like that. That doesn't make sense. The longest delay we can do with this would be if we initialize timer 0 to 0, and that would take 256 microseconds. So what can we do if we want a longer delay? The easiest thing we can do is we can switch from treating timer 0 as an 8-bit value to a 16-bit value. And that's where we're thinking of this as a pair of registers, timer 0 low, timer 0H. And if we're in 16-bit mode, then it overflows at 65,536. So now if I want to interrupt after 500 ticks, I just initialize my 16-bit timer 0 register to what? 65,036. And after 500 increments, it'll hit this value overflow requesting interrupt. So we can affect a longer delay by specifying that this should be a 16-bit register instead of an 8-bit. And how do we do that? Well, there's more bits and more registers that we can set to 1 or 0 to control this behavior. And we'll look at those in a few minutes, but I'm working at the conceptual level still. Okay, so we can get a longer delay by saying, make this a 16-bit register, overflow at this bigger value instead of this 8-bit value. But what if you wanted to delay longer than 65,536 microseconds? What if you wanted to wait 30 minutes before an interrupt was generated? Well, there's a mechanism for dealing with that also. And so now we have to look at this question of I picked 1 microsecond, but what actually is it that determines how often this register gets incremented? And that's the left part of this picture, this business over here. So remember, this line right here going to timer 0, that's the clock input on the counter. Right? When this line ticks, timer 0 gets incremented, goes up by 1. But what causes a tick to occur on here? Well, there's a couple of things. One thing we can do is we can use the instruction clock. Okay, so F oscillator, this is the system oscillator. This is the 32 kilohertz one that we have by default on the PIC. When you divide it by 4 and you get that 8,000 kilohertz, that's the instruction cycle clock. Remember, we execute 8,000 instructions per second, roughly, if they're most instructions. 8,000 per second. That's the first version of what increments this register. It will increment once per instruction. So 8,000 instructions per second, 8,000 increments per second. So on our default PIC processor, the usual clock going into here is pretty slow, right? It's incrementing 8,000 times a second, so it's an 8,000th of a second, or 125 microsecond. So I don't want to get too bogged down in math. So default instruction clock is 8 kilohertz. So one instruction takes 1/8,000th of a second, which is 125 microseconds. I almost wrote microfarad there. That's bad. 125 microseconds per instruction. So that's how long it takes to increment timer 0, 125 microseconds. So if I go back here and I set my timer 0 to 255, I'll get an interrupt after 125 microseconds. If I set it to 254, it'll take 250 microseconds. If I set it to 246, it'll take 1.25 milliseconds, 1,250 microseconds. So what we're doing is we're trying to generate an interrupt after a certain amount of real-world time has passed. But we have to translate that into the number of instruction cycles. And so you need to know your clock frequency. And by default, our clock frequency is 32 kilohertz, which divides by 4 to give us an instruction cycle frequency of 8 kilohertz. But we can set up the PIC processor to say, hey, let's use a 4 megahertz clock, which means we have a 1 megahertz instruction cycle, so we get 1,000,000 instructions per second. That's 1 microsecond per instruction. That's 1 microsecond to increment timer 0. And we'll talk about timers in more detail on Tuesday, probably. I don't think I want to get into it today. But I'll give you some homework questions to start looking at, and we'll talk about controlling the clock of the PIC processor on Tuesday. But by default, sort of, the thing that's causing this thing to increment is a tick of the instruction cycle clock. Okay, so let's stick with the default 32 kilohertz system clock, 8 kilohertz instruction cycle clock, 125 microseconds per instruction. So every 125 microseconds this increments. Well, that's going to get us a longer delay. 8-bit register, 256 times 125 microseconds, that's a pretty good delay. 16-bit register, we can go up to 65,536. I'm pulling out my calculator right now. Times 125 microseconds. That's about 8 seconds. So we could get an 8-second delay out of our PIC processor by saying, let's make this 16 bits. Let's initialize the timer 0 register to all 0. And it'll take about 8 minutes before this 16-bit register overflows. And then when that happens, it'll generate an interrupt request. And what would you do with that? I don't know. You're going to jump to location 8 or 18. You sound an alarm, or you change an LED, or you increment a counter or something like that. And if you want this to happen repeatedly, you reload whatever value you want in timer 0. You clear the interrupt flag, and you do a Redfee, which will re-enable interrupts. And it'll wait for that period of time again, and then generate another interrupt request. Alright, so we can get up to 8 minutes on our default PIC processor. What if we want a longer period than that? This is where we get into the last detail, which is this thing called a prescaler. And a prescaler basically lets us divide down this instruction cycle clock even further. So let's go back to our earlier case. Let's suppose 1 microsecond per instruction cycle. So we increment every microsecond. Okay, so suppose the instruction cycle equals 1 microsecond. And let's go with 8 bits. So we overflow at 256. So here's the timer 0 initial value. And here's the time till an interrupt. All right, so let's just repeat a few of these values from here. If I set timer 0 to 246, I'll get an interrupt after 10 microseconds. If I set timer 0 to 56, I'll get an interrupt after 200 microseconds. Okay, there's another thing we can set which is called a prescaler. And if the prescaler is 1-to-1, then everything we said here is completely correct. But we can set other prescaler values. So suppose I set a prescaler of 1-to-2. It doubles the amount of time till the interrupt. Okay, so there's another thing we can set in some special function registers called a prescaler. And if we set it to say 1-to-2, it will double the amount of time it takes to generate an interrupt. If I set my prescaler to be 1-to-4, and I set my timer 0 to 246, instead of taking 10 microseconds, it'll take 40 microseconds. If I set my initial value to 56, instead of taking 200 microseconds, it'll take 800 microseconds. So I can further increase the amount of time it takes to generate an interrupt request by setting a prescaler to something other than 1 to 1. Okay, so conceptually you've got all the pieces now for timer 0. It's quirky, I'll admit that up front, right? It's not like setting an alarm on your phone. But it's doing the same thing, it's just the interface is not a very user-friendly one. Right? You have to count down from either 256 or 65,536, and you have to adjust a prescaler, and you have to know what the system clock is and all this other stuff, right? But those are the steps of it. And so that's what this business is over here. You have an input coming in and it goes through this prescaler, which basically divides it down and slows down how often this thing will increment. Additionally, if we really want to go crazy, instead of using the instruction cycle clock, we can put in our own clock signal. And so by setting this bit T0SE, we can put a value on this pin, RA4 TOCKI, that's timer 0 clock input, and it'll use that as our clock that is used to increment this timer register. And we do this typically if we want some particular value to work with, or maybe we want a faster clock or a much slower clock. Alright, so let's look at a few of the details on the registers, and then I'll run you through some homework quickly to start working on, and I'll let you get to your labs again. Here we are. Alright, so really one register to worry about. So bit 7, timer 0 on, that's what turns on the timer. Okay, if you set that to 0, none of this stuff happens. The incrementing doesn't happen, the interrupt requests don't happen, it turns the whole system off. Okay, so when you want to use the timer, last thing you do usually is turn on bit 7 of T0 con. Bit 6 says, do we want to do 8 bits or 16 bits? Do we want that overflow to happen at 256, that's an 8-bit mode, or at 65,536, that's the 16-bit mode? So you set this bit, T0 8-bit, to 1 or 0. 1 makes it 8 bits, 0 makes it 16 bits. Bit 5, T0CS, says, what do we want to use as the clock that's being used to drive this whole incrementing business? We've been talking about using the instruction cycle clock. Set this bit to a 0 to use the instruction cycle clock. If you wanted to supply your own clock from outside, you would set this bit to a 1. We're not going to do that in here. We'll stick to the instruction cycle, so that bit's going to be a 0. If we're using an external clock, we can say, do we want the event to happen on the rising or the falling edge? That's what this pin controls. Doesn't matter for us. Alright, if you do not want a prescaler, if you want the prescaler to be 1 to 1, so you're just getting this straight, subtract this from the rollover point, that's how long it takes. If you do not want a prescaler, set this bit 3 to be a 1. Alright, and then it's a 1 to 1 prescaler value. And these other bits are ignored. But if you want a prescaler, set bit 3 to a 0. That says we're using a prescaler, and then these 3 bits, 2, 0, 2, 1, and 0, get set to one of 8 possible values to set up a prescaler. Largest prescaler we can have, 256. So what used to take us 8 minutes, we can cause to take 8 times 256 minutes. So quite a few hours. And remember, the idea here is you set this stuff up, you load magic values into here, you set up your interrupts so that timer 0 interrupt request causes a jump to location 8 or 18. You turn the system on, and you can go off and do whatever you want. And 16 hours later, an interrupt request will come in, and you'll suddenly jump to location 8. And at that point, 16 hours or whatever you set the timer for has passed since you started the system, and you can do whatever you want to do. On most computers, we have a clock. My clock is up here in the upper left. I have seconds on there, and it's showing 31, 32, 33, 34. How does it know what time it is? Because every probably, fraction of a millisecond, there's an interrupt generated. And there's code in the operating system that increments a counter, and when that counter gets to the point where it knows a second has passed, it increments another register which stores the number of seconds. And when that reaches 60, it clears it and increments another register which represents the number of minutes, and so on. And this field up here that's showing the date and the time reads those registers and displays them as a set of pixels on my screen. It's all interrupt driven. Alright, so that's timer 0, and timer 0 is enough to worry about for now. We'll deal with the other timers on Tuesday. Really quick look at the interrupt registers associated with these. So intcon has the timer 0 interrupt request flag and the timer 0 interrupt enable. And those are probably the main two you need to deal with. I don't think there's any more actually, because I think timer 0 may always be high priority. Nope, timer 0 can be high or low. So intcon 2 lets you set timer 0's priority, defaults to high priority. That's a value of 1. Alright, so let's pick out some homework questions. So think about these questions starting from 58. Okay, 58, assume the system clock is 4 megahertz, divide by 4 to get an instruction frequency of 1 megahertz. How long does one instruction take? That's 1 microsecond. Okay, that's what we've been playing with. How long would 100 instructions take? How many instructions would you execute in a tenth of a second? Now do the same thing for a 32 kilohertz clock. So these are practicing thinking about frequency and period. Right? Frequency is how many times something happens per unit time. Period is how long something takes. They're reciprocals. So play around with those, ask questions about them. 65, some instructions take longer than others. Look at table 20-1, see how many cycles a branch instruction requires. We already did this when we were talking about delay loops, but this is a chance to do it on your own. Okay, so think about this. How many cycles do the last two instructions take? And this is basically taking apart those timing loops we've been using in the labs. Okay, so I'd like you to look at those. So that's questions 58 through 70. And then some questions on timer 0. So this is playing with, here's the system clock frequency, here's the instruction clock frequency. Prescaler 1-to-1, 16-bit operation, here's an initial value for timer 0. How many times does this increment before it overflows? How many instruction cycles does that correspond to? How much time does that correspond to? So this is what we've been doing over here, right? And then what we did here with changing the prescaler. So different versions of this. This should say 71 through 73 instead of 14 through 16. So repeat these three questions, assuming this value for timer 0, this value for timer 0, and then for different prescalers. And then for an 8-bit mode with a prescaler 1-to-4. And then take a look at the T0 con register and see what values you would load in for questions 80 and 81. Alright, so start working on those, bring questions to class. I will hop over to my office hours, go ahead and keep working on your lab if you haven't finished it, and hit me up with questions in there. Have a fantastic weekend, and I will catch you next time.
Thank you.